Welcome to the presentation of TardisDB, extending SQL to support versioning. The highlighted example is Wikipedia, which needs version control to track the history of an article. It needs 3 tables, one table page to store the title and one table revision to track the history. Both reference to the table page content, which stores the actual content. So we see version control inside of database systems needs to support referential integrity and should therefore include multiple tables within a version. We want to support implicit version control inside of database systems, and therefore we need an SQL integration as well. This talk is structured as follows. First, we will present the SQL integration with statements for branch creation and version retrieval. Then we present the concept of TardisDB, an integration into a main memory database system. Afterwards, we will evaluate the performance using a benchmark using text compression based on Wikipedia. The SQL integration is downward compatible to SQL 92. To show that we support reference constraints, we first create 2 tables with a reference in between. If we want to insert tuples without anything added, we say this concerns the master branch only. Then we introduce a statement for branch creation that preserves the current database state. If we want to insert or retrieve tuples from a certain branch, we have to add the keyword version after the table name to identify a certain version. This allows querying different versions within a branch, and afterwards, if we want to delete a branch, we release memory using the statement delete branch. We now present the concept behind TardisDB. TardisDB, time and relative dimensions in databases, supports 2 dimensions, one for inserts and one for updates. We use bitmaps for insertions and deletions. The bitmaps for every branch indicate included tuples. We reuse multi-version concurrency control for updates. Every tuple is marked by the creator branch for table scans. We have one prioritized master branch for which we need no further operations, which is stored in a column store. Updates happen in place. Previous versions are chained in buffers. Let's show a short example. We first insert tuples in the master branch. Afterwards, we create branch 1. If we now modify a tuple in the master branch, it does not affect tuples in branch 1. If we modify tuples in branch 1, it only affects tuples in branch 1. We can also create another branch and update the tuples concerning only branch 2. Afterwards, we can also create a branch 3 and delete tuples. So these tuples are no longer visible in branch 3 as the bit is unset. If we want to retrieve a tuple, it works as follows. Timestamp TS for every branch and every tuple indicates whether a tuple is included or not. At first, we have to check the bit in a bitmap here on the left. If the bit is set, we can evaluate the predicate active. Active evaluates to true if either the branch has created the tuple itself, or it evaluates to active if an ancestor branch created the tuple before branching took place. Afterwards, we take the latest active entry, the one with the highest timestamp. Let's have some examples. A in branch 3. The bit is not set, so this tuple is not visible. C in branch 3 is visible, and as we updated it here, this is the latest active tuple, so it returns C14. A in branch 1. Branch 1 has a timestamp of 5 when it was created. A6 was updated afterwards, so the latest visible entry is A1, and this one is returned for branch 1. To benchmark different approaches and TardisDB, we created the TARDIS benchmark. It is based on Wikipedia, based on the schema of MediaWiki with tables for page, content and revision. XML page dumps as input allows flexible workload. We compare two text compression methods, snapshot, the default, which stores every change as a whole, and diff, that stores changes to the latest version as a delta of differences. We measure three operations: insert, to insert pages and to compute the deltas; retrieve latest, to retrieve the latest page version, the default use case for Wikipedia; and retrieve first, that needs to apply all data to retrieve the first version. We benchmarked using the full page edit history from August 2018. Let's have a look at the insert performance and the space requirement. As we see, if we store the snapshots, we need 100% of the original size, which is obvious. But when we wanted to compute the differences, this needed more time, as we need to compute all differences. Let's have a look on the retrieve performance, on retrieve latest and retrieve first. As we see, TardisDB was optimized for this workload, and we see that TardisDB allows the most operations per second, so it is the fastest. This is also the case for retrieving the first version, as TardisDB is highly optimized for retrieving versions within a chain. To summarize, TardisDB showed the best performance for retrieving the latest version. Nevertheless, Git showed the best compression and also allowed good retrieval times. Lighttree was fast but only allowed up to 1024 branches and consumed a lot of space. Our diff-based approaches consumed 90% less space than a snapshot approach. Here on the left we see the measurements summarized. On the left we see TardisDB, which is always the fastest, but it also consumes nearly 100% of the original space. So as future work, we need to combine version chains with difference-based compression methods to reduce the space consumption. And also TardisDB only allows one user at a time. So in a future work, we need to enable multi-version concurrency control within TardisDB. I want to show you two examples how versioning within database systems works. One example uses a university schema. Another one is based on Wikipedia data. In the first example, we create one relation for lectures and one for professors that need an update every term. So we want to update the tuples on the master branch. Before each update, we want to preserve the state at the end of a semester as a separate branch. Here, we create the two relations and preserve the initial state as branch empty. Afterwards, we can fill the tables with data. In the second term, for example, we want to add a new professor together with a new lecture. So we first preserve the state of the first semester, then we can update the master branch. Afterwards, we can preserve this state again. Also, we create a branch called sabbatical for temporary changes. There we can edit the lecturer, so this concerns this branch only. The lineage of all branches is depicted in the middle. When we now query the branch sabbatical, we will see only lectures held by Russell. The branch empty was created before any tuples have been inserted, so no tuples appear. But when we query the first term only, we can see only the lectures held by Socrates. For the second term, both professors are visible. Wikipedia normally needs 3 tables, one for the page information containing the title, one for tracking the history, and one for the actual content. With versioning, we only need 1 table anymore. For the Wikipedia example, we first show the current schema that we fill with data from a CSV file. When we want to edit an article, we have to touch these 3 relations. In our extended SQL, 1 relation is enough. Feel free to test our database system as the link is publicly accessible. Thank you for your attention.